Welcome back. In lieu of time constraints, I'm going to discuss Avogadro's law and Graham's law in this video, and I'll make a separate video for Dalton's law of partial pressure, simply because it might just take a little longer to explain the concept. All right. Now, before we get started, I've already introduced you to the idea of standard temperature and pressure, and that is a condition that constitutes the pressure is 1 atmospheric pressure, like you see here, and then the temperature is 273 kelvins or 0 degrees Celsius. So 1 atm and 0 degrees or 273 Kelvin constitutes standard temperature and pressure. So the question here asks you, whenever we are discussing STP, we have to write the standard ideal gas law equation, which is PV equals nRT. And the question is asking how much volume does 50 grams of nitrogen would occupy at STP, right? Given the fact we know the condition is STP, we know the pressure is 1 atm, temperature is 273 Kelvin. Keep in mind, you got to use Kelvin, otherwise your answers would be different, right? We want to find volume. That's what we have to find. We know R is 0.0821 liter dot atmosphere over mole dot Kelvin, and our pressure is, okay, that is given. So N is something we have to find, which is, if you take 50 grams of nitrogen, the molar mass of nitrogen gas is 28 grams. So see, the idea of being able to convert moles to grams or grams to moles is very, very important. So that's 1.79 moles. So we know now N value is 1.79 moles. So if we solve for V, which would be nRT over P equals 1.79 times 0.0821 times 273 over the value of P is 1. So if you put all that together, it's 40 liters or 40.1 liters. And that's how you deal with an Avogadro's law, because the reason that is because 1 mole of any gas occupies, and another information that I'd like to give you is 1 mole of a gas at STP equals 22.4 liters. This is a constant. You would have to memorize this. I am not going to give this to you on the test. 1 mole contains 22.4 liters. So down the course, I will work out another problem, maybe in a separate video, where I would expand on this concept. But this is a statement. So 1 mole of any gas at STP occupies 22.4 liters. Now, this is another interesting problem. What is the density of chlorine gas at STP? At STP, we can, if you are interested how I derive this formula, you can just ask me in class. But there's a shortcut, which is density equals molar mass, M is molar mass, times P is in pressure, which is in atm, R is gas constant, and T is in Kelvin. So all we have to do now is simply apply all the numbers in here. Molar mass of chlorine is about 70 grams per mole, times pressure is 1 atm over R is gas constant, which is 0.0821, times temperature is 273 Kelvin. Now, you can only use this formula when STP is persisting. Otherwise, I wouldn't recommend you go this route. Of course, again, like I said, if you want to know how I derive this equation, you can ask me, but I will give this equation to you on the test. So you just have to apply and get the answer. So it'll be 70 divided by 0.0821 divided by 273. So that's 3.1 grams over. Now, if you notice, this answer would be in liters, okay? I guess if the unit desired is in grams per liter, then you can stop here. But if I specify the density to be grams over milliliters, then you can convert the liters to, so that I'll do this here. So if you want, so this is 3.1 grams over liter. Say I want the answer to be in milliliters, then you do this extra conversion step. So it'll be 3.1 over 1,000, right? That's what you're doing, which would be 0.0031 grams per milliliter. How do I know it's liter? Because the gas constant is in liters. So be careful, 3.1 grams per liter is not same as 0.0031 grams per milliliter. All right, moving on. Now we're on to Graham's law. And if you remember, Graham's law is rate of R1 of one gas over rate of second gas equals molar mass of the second gas over molar mass of the first gas. It's opposite. If you put whatever the gas you put, the molar mass of that gas should go here. So it's asking, determine how fast can helium effuse compared to nitrogen gas. So let's say you put helium and nitrogen gas in the same balloon. Which one would effuse faster if you put a hole? And how fast would it be effusing compared to, how fast would helium would effuse out of the balloon compared to nitrogen gas? Okay, so let's call R1 as our helium, okay, and R2 as our nitrogen gas. That means the molar mass of nitrogen should be on the top, which is 28, and molar mass of helium is 4. So if you do the math, root 28, square root of 28 or square root of 4, this whole thing is square root of 7, which is about 2.6. Okay? So that what this means is R1 of helium equals 2.6 times R2 of N2. What does this mean? It means that helium can effuse out of the balloon at almost 3 times faster than nitrogen. So helium would come out first from the balloon before nitrogen can come out. And how fast would it be happening? Almost 3 times as fast. Like, so if you put equal volumes of helium and nitrogen in a balloon and you put a pinhole in the balloon, then helium would come out first, followed by nitrogen. But how fast would helium be coming out of the balloon compared to nitrogen would be almost 3 times. Okay, I'm just rounding off the 2.6 to a 3. You do not have to do this. If you just stop here, that'll be perfectly fine. But I just went that extra step to explain to you what is really happening. So this is Graham's law, which primarily deals with effusion. Effusion is when you have a small hole in a balloon or bag or whatever you're dealing with, a container, and something has to expand from a smaller volume to a larger volume through a fine hole. That process is called effusion. All right, so this is where I want to stop on the concept of Avogadro and Graham's law, and in a separate video I'll come back and talk about Dalton's law of partial pressure. That's because that's very similar to what you learned in Raoult's law. All right, so that's why I want to keep it as a separate video. All right, so stay tuned.